In the last talk, we learned how to count disease, prevalence, incidence, and case fatality rate. Now we take the next step, measuring the relationship between an exposure and a disease outcome. This is the heart of epidemiology. We don't just want to know how much disease exists, we want to know why. Is this risk factor actually associated with this disease? And if so, how strong is that association? To answer those questions, we use measures of association. The three most important ones you'll encounter in the veterinary literature are the risk ratio, the odds ratio, and the hazard ratio. They're related. They're sometimes confused with each other, and choosing the wrong one or misinterpreting one as another leads to real errors in how you read and apply research evidence. By the end of this talk, you'll be able to define, calculate, and interpret all three, understand when each one is appropriate, and connect them to the broader concept of absolute versus relative risk. Let's go. All three measures of association are built from the same fundamental comparison. How does disease frequency differ between animals that were exposed to a risk factor and animals that were not? The 2x2 table is our tool again, but now the rows represent exposure status rather than test result. The exposed group is animals that had the risk factor, a specific feed, a pathogen contact, a management practice, a genetic trait, whatever we're studying. The unexposed group is the reference, animals without that risk factor. Cell A, exposed animals that develop disease. Cell B, exposed animals that don't. Cell C, unexposed animals that develop disease. Cell D, unexposed animals that don't. From this table, we can calculate the risk of disease in each group. A divided by A plus B for the exposed, C divided by C plus D for the unexposed. We can also calculate the odds of disease in each group. A divided by B for the exposed, C divided by D for the unexposed. The difference between risk and odds is subtle but important, and it becomes the foundation for distinguishing the risk ratio from the odds ratio. The risk ratio, also called relative risk, is the most intuitive of the three measures. It's simply the ratio of the risk of disease in the exposed group to the risk of disease in the unexposed group. In our example, BVDV positive calves had a 30% risk of developing BRD. BVDV negative calves had a 10% risk. Relative risk equals 0.3 divided by 0.1, which equals 3. How do you interpret that? You say it out loud. BVDV positive calves were 3 times as likely to develop BRD as BVD negative calves. That's it. Simple, direct, and clinically meaningful. RR of 1 means equal risk. The exposure isn't associated with the disease. RR greater than 1 means the exposure is associated with increased risk. RR less than 1 means the exposure is associated with decreased risk. It's protective. A vaccination study with an RR of 0.3 means vaccinated animals are 30% as likely to develop disease as unvaccinated animals, a 70% reduction in risk. The risk ratio is the preferred measure of association when you can directly observe and calculate incidence proportions in both groups. This happens in cohort studies, where you follow exposed and unexposed animals forward in time and count who gets sick. It's also appropriate for randomized controlled trials, which are essentially prospective cohort studies with randomly assigned exposure. The critical requirement is that you must know the denominators, how many animals were in each group, so you can calculate the true risk in each group. Ratio is where students often get tripped up, partly because odds are less intuitive than risk, and partly because the OR and RR look similar but are not the same thing. Let's start with the concept of odds. Odds are simply the ratio of the probability of an event happening to the probability of it not happening. If the risk of disease is 30%, the odds of disease are 0.3 divided by 0.7, which equals 0.43, or equivalently 43 to 100, or about 3 to 7. Risk and odds are related but different. The odds ratio is the ratio of the odds of disease in the exposed group to the odds of disease in the unexposed group. There's a beautiful mathematical shortcut. OR equals A times D divided by B times C, the cross product of the 2 by 2 table. In our BVDV example, OR equals 45 times 180 divided by 105 times 20, which is 8100 divided by 2100, which equals 3.86. Compare that to the RR of 3.0. The OR is higher, and this is always the case when the disease is common. The OR exaggerates the association compared to the RR when disease prevalence is high. However, and this is critical, when the disease is rare, the odds of disease and the risk of disease become very similar. When disease prevalence is below about 10%, OR and RR are approximately equal. This is called the rare disease assumption, and it's why the odds ratio is still useful and widely reported, even though it's less intuitive than the RR. How do you use the OR? In case control studies, where you start with cases and controls and look backward at exposure history. You cannot calculate true incidence proportions because you've intentionally oversampled cases. The OR is the appropriate measure in that design. Logistical regression, the statistical workhorse of observational epidemiology, also produces odds ratios. So when you're reading a case control study or a logistic regression output, you're reading ORs, not RRs. Don't interpret them as risk ratios when the disease is common. Hazard ratio is the measure of association used in survival analysis, a family of statistical methods designed for time to event data. In veterinary medicine, survival analysis is extremely common. Time to death in cancer patients, time to relapse after treatment, time to recovery, time to first lameness episode in a dairy cow. Anytime the outcome is not just did it happen, but when did it happen? You're in survival analysis territory. The hazard is technically the instantaneous rate of the event occurring at any given moment, given that the animal hasn't experienced the event yet. You can think of it loosely as the probability of the event happening right now. The hazard ratio compares this rate between two groups across the entire observation period. In our oncology example, dogs treated with tosiranib had a hazard ratio for tumor progression of 0.42 compared to placebo-treated dogs. That means tosiranib-treated dogs progressed at 42% the rate of untreated dogs, a 58% reduction in the hazard of progression. This is a clinically meaningful effect. Note how the interpretation differs from RR and OR. We say rate rather than risk because a hazard is a rate, not a proportion. And because survival analysis accounts for the timing of events and for censoring animals that leave the study before the event occurs, it's much better suited to clinical trial and longitudinal study data than a simple risk ratio would be. HR less than 1 means the exposed or treated group experiences the event at a lower rate. In a treatment context, that's a beneficial effect. HR greater than 1 means they experience it at a higher rate, harmful effect. HR of 1 means no difference. One important caution, like the OR, the HR is not the same as the RR, and interpreting it as such can be misleading, especially when event rates are high or when the hazard ratio changes over time. We'll look at how to read Kaplan-Meier curves in Talk 3.5 when we cover survival analysis in full. Here's a side-by-side comparison that I want you to use as a reference. When you're reading a paper and you see a measure of association reported, the first question to ask is, which one is this? And is it appropriate for the study design and outcome? Risk ratio, cohort studies and RCTs with binary outcomes and fixed follow-up times. It's the most intuitive. A BVDV positive calf is 3 times as likely to develop BRD. That's exactly what the number said. Odds ratio, case control studies and logistic regression. Binary outcomes, less intuitive, but essential because case control studies are extremely common and logistic regression is everywhere. Approximately equal to RR when the disease prevalence is below 10%, but increasingly divergent as the disease becomes more common. Hazard ratio, survival analysis, time to event outcomes, accounts for the timing of events and for censoring. Less intuitive than RR, but more powerful for longitudinal data. In oncology, cardiology, and any study involving time to death or time to recurrence, you're reading hazard ratios. One rule that applies to all three, they should always be reported with a confidence interval. A point estimate without a confidence interval tells you the best guess, but nothing about the precision of that guess. We'll cover confidence intervals in detail in Talk 3.4. For now, just remember a measure of association without a confidence interval is incomplete. This slide addresses one of the most practically important concepts in all of evidence-based medicine, the distinction between relative and absolute measures of risk, and why you need both to make good decisions. Relative risk tells you how many times more likely the event is in the exposed group compared to the unexposed group. It's a ratio, so it's always relative to a baseline. The risk difference, also called the absolute risk difference or attributable risk, tells you the actual numerical difference in risk between groups. Risk in exposed minus risk in unexposed. Here's why this matters so much. Consider 2 scenarios, both with an RR of 2. A doubling of risk with exposure. Scenario 1, a rare disease. Risk in the unexposed is 1%. Risk in the exposed is 2%. The RR is 2, exposure doubles your risk, but the absolute risk difference is only 1 percentage point. In a herd of 1,000 animals, eliminating the exposure would prevent 10 cases. That might or might not be worth the intervention cost. Scenario 2, a common disease. Risk in the unexposed is 30%, risk in exposed is 60%. The RR is still 2, but now the absolute risk difference is 30 percentage points. In a herd of 1,000 animals, eliminating the exposure would prevent 300 cases. The same relative effect size has a dramatically different practical importance. Headlines and press releases love relative risk because it sounds impressive, doubles your risk. But without knowing the baseline risk, a doubled risk could mean going from 0.001% to 0.002%, or from 30% to 60%. These are not the same public health problem, and they don't justify the same level of intervention. Always ask for both relative and absolute measures. We'll come back to this when we cover NNT in Talk 3.3. Here's the summary. 3 measures, RR, OR, HR, each appropriate for different study designs and outcome types. All share the same null value of 1, and all carry the same directional interpretation above and below 1. Always pair them with a confidence interval, and always accompany a relative measure with an absolute risk difference, or number needed to treat, so that the practical significance is clear. In the next talk, we cover NNT and NNH, the number needed to treat and the number needed to harm, which are arguably the most clinically meaningful ways to communicate treatment effects, and which flow directly from the risk difference. Pause the video and try your hand at working through the question. We'll then work through it together. Let's work through this carefully. First, populate the table. Exposed, blanket DCT. Mastitis, yes, equals 24. Mastitis, no, equals 176. Total equals 200. Unexposed, selective DCT. Mastitis, yes, equals 36. Mastitis, no, equals 164. Total equals 200. Question 1. Relative risk. Risk in the exposed equals 24 divided by 200 equals 0.12 or 12%. Risk in the unexposed equals 36 over 200 equals 0.18 or 18%. Relative risk equals 0.12 divided by 0.18 equals 0.667. Plain language, cows receiving blanket dry cow therapy were 0.67 times as likely, or about 33% less likely, to develop clinical mastitis in the first 30 days in milk compared to cows on selective dry cow therapy. Because RR is below 1, blanket DCT is protective relative to selective DCT in this study. Question 2, OR, cross product. OR equals A times D divided by B times C equals 24 times 164 divided by 176 times 36 equals 3936 divided by 6,336 equals 0.621. Is it close to the RR of 0.667? Somewhat. They're in the same direction and approximate range, but they're not identical. Mastitis incidence in this study is 12 to 18%, which is not extremely rare, so there is some divergence between OR and RR. The OR overestimates the protective effect slightly, 0.621 versus 0.667. This illustrates that the rare disease assumption doesn't fully hold at these prevalence levels, and the OR and RR should not be used interchangeably. Question 3, risk difference. RD equals 0.12 minus 0.18 equals negative 0.06 or minus 6 percentage points. Blanket DCT reduces the absolute risk of mastitis by 6 percentage points. In a herd of 200 cows, that translates to 12 fewer cases of mastitis per lactation. 200 times 0.06 equals 12. The RR told you the relative reduction in risk. The risk difference tells you the absolute magnitude, which is what the producer needs to know to weigh against the cost of blanket versus selective treatment. Question 4. Both colleagues are correct. They're reporting the same finding in different frames. The first colleague is expressing the relative risk reduction. 1 minus 0.667 equals 0.333 or 33%, the relative reduction in mastitis risk. The second colleague is expressing the absolute risk reduction, 6 percentage points. Neither number is wrong, but they communicate very different things. For a producer deciding whether to change protocols, the absolute number, 6 fewer cases per 100 cows, or 12 fewer cases in a 200 cow herd per lactation, is far more actionable. It can be directly compared to the cost of blanket DCT versus selective DCT and the cost of a mastitis case. Relative risk alone doesn't give you that. This is the core of the NNT concept we'll develop in the next talk.